Hello and welcome to another episode of Recently in the Support. Today I would like to show you a possibility how you can apply a specific force or a specific moment to an assembly where the contacts are initially opened. That's typically a problem when you do that force controlled, but I will show you a possibility how to do that in a very stable manner. Let's see how that works. So let's take, for example, this shaft with this hub, and we see that there are gaps on the left and on the right side. So we have gaps on both contact sides of the tooth. The stiffness times the deformation is the force. That's the formula. And so if we give the force, the torque, we will have to invert the stiffness matrix. But with the two gaps, the stiffness matrix, the determinant of the stiffness matrix is 0. And that is a problem that will not work. If we have a look at the initial formula, stiffness times deformation is force. That means if we don't give the force, but the deformation, we will not have a problem. So let's give the rotation instead of the moment. We can do that by adding two nodes. One node is applied to a distributed coupling, and the other node is applied to a connector. Then we define a rotation on the left side, on the left node, which will be transferred to the distributed coupling. But what if we would like to have 10 Newton meter in one direction and 20 Newton meter in the other direction? That's no problem. The connector gets a behavior, and the behavior is a nonlinear spring behavior with 10 Newton meter as maximum in the one direction and 20 Newton meter in the other direction, and the torque stays constant when it reaches the maximum value. So that's the idea behind it, and no matter how far we rotate this node, the torque will always stay at this maximum value. Let's see how we do that in Abacus. Here we have the hub in green, and we have the shaft in light gray. And this one reference node, RP Nabe, will be attached to a distributed coupling, and RP Lasteinleitung is attached to a hinge connector. Here you see the distributed coupling will be glued to the holes of the hub, and the reference node will steer this one. And the hinge is attached to RP Lasteinleitung, and it gets the connector behavior, which is an elasticity, a nonlinear elasticity. And we have 10 Newton meter in the negative rotation direction and 20 Newton meter in the positive rotation direction. That's all. That's all the magic behind it. It's nothing more. And this will run very stable because it's not a force-controlled calculation. It is a displacement-controlled calculation. And the result you can see here, if we animate it, you see that the gaps, they are opening and closing. And in the middle of the change of the direction, we will have both gaps opened. And even though they are opened, the calculation runs very stable. Maybe I put a cut in there. I'm using the set plane and moving it a bit forward. And then we can see it a bit better, how the contacts are opening and closing. So that seems to work. The rotation is applied to the hub. That's working, but the question is if the torque is applied correctly. No problem to find that out. I will just add a second viewport, and I will tile the viewports vertically. So on the right side, we will now add the characteristics. So we put an XY plot here from a field output, and as a field output, I'm selecting the reaction moment in Z direction, RM3, at the node set RP last. If I plot it, you can see, well, it seems to work. We have 20 Newton meter in the positive rotation direction, and we have 10 Newton meter in the negative direction. And if I link the two viewports, you see that We can directly correlate the picture we see on the left to the characteristics we see on the right. And you see that at the transfer points where both gaps are opened, the torque is 0. So everything's working fine. And now the question is, maybe can we have also a look at how the connector behaves? For this purpose, we have to activate the view, the connector view, in the view menu, ODB display options, and then entity display. And there is connector, show connectors. If we apply that, you can see the coordinate systems, how they are turning. And that shows that the coordinate systems, they keep turning because we rotate the nodes permanently. But even though they are keeping rotation, the torque stays constant. So everything's working like we expected. And that's a very easy way, which can be used for many purposes, not only for rotations, but also for translations. So feel free to use that method and, well, tell me how it works. I'm very interested in getting to know how your experience with that method is. I have a very good experience with it, so have fun using it and see you next time. Goodbye.